Hello everyone. I am Brajesh Kumar from Udaipur Solar Observatory, which is a part of Physical Research Laboratory in India. And I'm very happy to present my work at the International Conference on Space Science and Technology, organized by the Space Education and Research Foundation, Ahmedabad. And this picture shows the island observatory of Udaipur Solar Observatory. And on this island, one can see two domes. This dome houses multi-application solar telescope of Udaipur Solar Observatory, which is a state-of-the-art modern telescope in India. And this dome houses another telescope, which is an old telescope. And this telescope is known as a SPAR telescope, which has been used for long for observing the solar activities. The large water body around this island reduces the ground heating and makes it possible to image the sun with sharp and focused images, because the ground heating is reduced, then there is less turbulence in the air, and then that helps in taking good solar images. Another thing is that Udaipur has more number of clear days over the year, and this two combination of having a large water body in the form of a lake and a number of more clear days over the year has made possible for solar observations, nice solar observations from Udaipur. Now the topic of my discussion is starts with a question: can major flares excite global waves in the sun? So we'll try to find an answer to this question as we progress in the talk. The outline of my talk is as follows. I will start with a brief introduction to the structure of the sun in the form of the internal and external layers of the sun. And then I will move to the discussions on discovery of 5-minute pulsations of the sun, which happened in 1962, and interpretation as trapped acoustic modes in 1970, which was a landmark in the field of solar physics, as it gave birth to a new branch of solar physics known as helioseismology. And soon after the discovery of these 5-minute oscillations on the sun, it was speculated by Wolff in 1972 that flares, which give rise to huge amount of energy in the solar environment, can induce oscillations in the sun. However, because of scarcity of uninterrupted observations dedicated to helioseismology, it was not possible. But then in 1995, the Global Oscillation Network group of telescopes around the world, where there are 6 telescopes around the world operational and observing the sun all the time. One of the nodes is also in Udaipur, which is dedicated to helioseismology. And soon after that, there was a space mission by NASA, which was flown in space, known as Solar and Heliospheric Observatory. So that was dedicated also for helioseismic observations. So using those observations, it was possible to discover sun-quakes, just like earthquakes in the sun, which was done in 1996. And later on, with the continuous flow of data, there are several evidences of flare-induced global waves in the sun, like in 2008, 2011, and 2017. Then I will discuss our current understanding towards flare-induced global waves in the sun, what we know till now with the studies done so far, and what are the future applications, which is in the form of having or understanding the astroseismic signatures of stellar flares. So now I will move to the discussions. This diagram shows the internal and external layers of the sun. The central part of the sun is known as core, which is the central engine of the sun, from where the sun derives its energy, which constitutes about 25% part of the internal layer of the sun. And the energy is liberated by thermonuclear reaction, where the fusion of hydrogen, 4 hydrogen into helium, plays an important role in the thermonuclear process. And each one reaction where the hydrogen fuses to helium gives about 26 mega electron volt of energy. So tremendous amount of energy is released in the core of the sun, making it possible for the central temperature of the sun of the order of nearly 10⁻⁷ Kelvin. Then the photons which are liberated in the core of the sun diffuses outward, and in this diffusion process, photon interacts with the matter. And then it takes years and years for the photon to diffuse out from the core of the sun. And this layer of the sun is known as radiative zone, because the process of energy diffusion is in the form of radiative transfer, radiative processes. Then the thing is, this constitutes about nearly 45% inner part of the sun. And then there is a convection zone of the sun just above it. Because what happens, the temperature gradient becomes, the temperature falls off very rapidly as we progress outward. And then because of this temperature falling very rapidly, there is instability in this zone and convection starts. So the temperature gradient is high in this zone. So energy in the form of convective eddies goes up, and then that convective eddy throws the energy at this boundary of the sun known as the surface of the sun, and the cooler plasma again settles down, comes inside. And this layer, which is between the radiative zone and convection zone, is highly disturbed, known as tachocline, because inner part behaves like a solid body, whereas this part behaves like a fluid. And this interaction at this boundary makes this layer very highly disturbed, known as tachocline, and this is supposed to be the seat of magnetic dynamo in the sun. So it is the place where the magnetic field is generated in the sun. And then this is the surface of the sun, the layer from where the maximum radiation escapes from the sun, known as photosphere. You can see here in the form of this picture, which depicts sunspots, which are the seats of high magnetic fields on the surface of the sun. And then these are cooler with respect to the surroundings, so it appears darker. And this layer is the surface of the sun. Just above the surface of the sun, the outer atmosphere is known as chromosphere. So where we see the activities like flares, flaring sites, or hanging cloud of gases known as prominences. The outermost layer of the sun is the corona, which is very tenuous, low density, but again the temperature is so high, of the order of 10⁻⁶ Kelvin. So the corona is normally not seen, but then when the moon blots the surface of the sun during the eclipse, then we see the corona. However, there are artificial ways too to see the corona from the space. There are missions in the space which occult which has occulted, and that occults the disk of the sun to see the coronal features and coronal activity. Okay, so now let us move ahead. So in 1962, it was a landmark in the field of solar physics when solar astronomers Leighton, Noyes, and Simon, they were trying to see the motion on the surface of the sun. They were observing using a spectroheliograph, trying to see the movement of upflow and downflow on the surface of the sun. So this depicts the position of the slit of the spectrograph, which is equivalent to something like 80,000 kilometers on the sun. And they found that the gases on the surface of the sun are moving upward and downward in a very periodic manner, giving a dominant 5-minute oscillation on the surface of the sun. And it was global in nature, happening everywhere on the sun. They followed this kind of motion on the surface of the sun, and it was happening all the day, allwhere on the solar disk. And the amplitudes of these oscillations were of the order of 400 to 500 meters per second. So this was a puzzle for these solar astronomers, and then once the experiment is there, then one has to give the theoretical explanation why this is happening. So then it took some time to interpret these oscillations. And it was Lavater and Stein in 1970 who proposed that acoustic modes or the pressure modes are stochastically excited in the convection zone due to high turbulence and sample different layers inside the sun. Here in this sketch, as we have already seen, this is the core of the sun. This is the relative zone. This is the convection zone. So in the convection zone, because of the high turbulence, high pressure changes, sound waves or pressure-driven acoustic modes are excited in the sun, which sample the different layers of the sun. So one can see here a wave which is sampling this layer of the sun, and this wave is going a little deeper, penetrating down inside, whereas this wave is shallower. So why it is happening? So what happens that once the wave is excited, then because the temperature is increasing downward, so it gets refracted and bends towards the normal. At the surface, because there is density stratification, then the density drops down very rapidly. So it works as a reflecting boundary for these acoustic waves. And then again, this wave is bounced back from the surface of the sun. Thus, it goes like this and rings the whole sun. And depending on the launch angle, this wave can penetrate deeper or it can penetrate shallower. So there are a variety of waves which are excited, and then these waves sample the different layers of the sun. Now this sun behaves like an open organ pipe, where looking at the size of the sun and open organ pipe, nearly 1 million of modes are excited in the sun. However, these are not coherent. But then the incoherent superposition of these 1 million modes gives rise to the dominant 5-minute photospheric oscillations of the sun. So that's what we see, the dominant 5-minute oscillations on the surface of the sun, which is happening all the time, everywhere on the sun. So these are global modes of oscillation on the sun. So soon after the discovery of these global modes of the sun, Wolff in 1972 proposed that the tremendous amount of energy produced during the flares can excite free modes of oscillation of the sun in the same way as the turbulent convection does in the sun. So I would like to discuss in brief about the solar flares. First, because the topic is concerned with the solar flares. So this picture is showing you the burning of gases in the solar environment in the chromosphere in a hydrogen alpha line during a flare, taken from US observations. This is on the disk, whereas this is happening near the limb, and one can see the ejection of plasma during the flare. So it is being thrown out during the flare, as well as the burning of the gases, and also the ejection of plasma, which goes into the interplanetary space and can cause space weather, can affect the environment around the Earth in various ways. So this is a limb flare. And these solar flares are highly explosive phenomena taking place in the solar atmosphere. These flares release tremendous amount of energy of the order of about 32 Earth and energetic particles moving with very high speeds. So because of this, Wolff suggested that large solar flares can stimulate free modes of oscillations with the sun. But as I mentioned, that this speculation was there for long, but then there were no dedicated missions for helioseismology for observing the solar surface motions. So then there was no conclusion on this for long. But then during one X2.6 class flare, which happened on 9 July 1996, it was Kosovichev and Zharkova who first discovered SUN-QUAKES. In SUN-QUAKES, one can see here, this is the Doppler image taken from MDI onboard SOHO. And one can see here the ripples. This is the site of the solar flare. And then one can see expanding ripples coming out of this flaring location. And as the time progresses, one can see the ripples are going ahead and ahead in the same way as if you drop a stone in a pond, you can see the ripples coming out from that point where the stone has dropped. Then it progresses outward and then it dies away after going to some distance depending on the energy. And one can imagine here, this is in the scale of megameter, how big these are. These are like similar way as we have earthquake in the sea, ocean, and then that creates tsunami, which goes thousands and thousands of kilometers ahead and produces high tides. And they propose that SUN-QUAKE is a manifestation of hitting of shock on the photosphere during solar flare. So they have given a model in which they say that solar flare, the energy which is there in the solar flare, that creates shock on the photosphere, and because of the shock, one can see these ripples in the sun, a similar way as it is there in the earthquake. So these are the models showing the impact of solar flares on solar surface flows. This model is showing the flare-driven seismic waves in the sun. So in solar flare, the magnetic field lines play a very important role. So these are the magnetic field lines connecting from the sunspots. And because of some reconnection happening in the solar environment, there is initiation of flaring phenomena. And from the flaring side, there is injection of accelerated electrons, which move along the magnetic field lines. These are highly energetic electrons and move along the magnetic field lines or gyrate along the magnetic field lines, emit gyrosynchrotron radiation. As well, when these highly energetic particles hit the chromospheric thick target, chromospheric plasma, then this plasma gets heated up. And then there is chromospheric evaporation. And this chromospheric evaporation, when this plasma goes up and cools down, when it settles down, it creates a high pressure region in this area. And what happens that the downward settlement of plasma creates a photospheric shock. As well, the energetic particles, when it hit the chromospheric plasma, then this gives rise to hard X-rays. which is a Bremsstrahlung radiation. And then some of the energetic particles also move towards the photosphere, can give a photospheric shock. So either the downward settlement of plasma, the evaporated plasma, can give a photospheric shock, or the energetic particles which are coming from the reconnection site and moving along the magnetic field lines, then it can also penetrate into the solar photosphere, giving a photospheric shock. And once this shock is there, from the shock point, sun-quake waves are excited, which can be seen here in the model, the ray path of acoustic waves excited by an impulsive source on solar surface. So this is sun-quake impact, and one can see here that the waves are traveling deeper into the solar interior, and depending on the launch angle, this will go penetrate deeper or shallower, and then move towards the surface, and wherever it knocks, it gives you the point of ripples. And with the progress of the time, one can see the ripples which is formed at the sun-quake impact point, as if it is moving, progressing with time. Apart from the sun-quakes, here is another example of flare-driven large velocity flows on solar surface, which was seen during X17.64b class flare, which happened on 28 October 2003. This was a major flare which happened in the solar cycle 22. Sorry, solar cycle 23. So here one can see the Dopplergrams from MDI. So this background image is the Dopplergram, and the contours here are the H alpha flare intensity contours, and one can see beneath the contours there are bright points in the form of black and white features. So these are locations of high velocity flows underneath the flare ribbons. So it was found that the velocity enhancements during the flare exactly matched the H alpha flare ribbons, and the peak velocity enhancement lagged the H alpha maximum by 1 minute, which is shown here in this plot. So the black solid line is for the Doppler velocity, and the dotted line is for the H alpha intensity. So one can see here the H alpha intensity maximum is here, whereas the Doppler velocity maximum is 1 minute later to H alpha intensity maximum. And the velocity flow is of the order of nearly 1.5 kilometer per second. So this seismicity has revealed that there is a lag of 1 minute between the H alpha maximum and the velocity maximum, showing that the time taken by the particles to travel from the flaring site in H alpha down to the photosphere has taken nearly 1 minute, which was shown in various models later on by various other researchers. For the same flare of 28 October 2003, same flare, we tried to see, that was local seismicity. We also tried to see if the flare has driven global modes in the sun. So we used disk integrated velocity signals from GONG observations to study the flare-induced global waves. Disk integrated velocity signals are just like the sun and star observations, which can give you proper information on the low degree modes or global modes. The dotted line is for the pre-flare and the solid line is for the flare. So this shows the progress of velocity with time, and then this is the comparison of power spectra. So the solid line is the power spectra during flare, and the dotted line is the power spectra during free flare. So one can see here, during the flare, there is enhancement of power in P mode regime as well as in high frequency regime, which shows that the flare has also induced global modes in the sun. This is another example of flare-driven local seismicity in the sun for one flare which happened in NOAA 10930 active region, and the flare was of the class X3.4, happened on 13 December 2006. So we used GONG observations to study this one. This is the intensity map showing the GONG observations. The white light image of the sun showing the sunspot, the umbra, penumbra, and the quiet region. And this is the RMS velocity map derived from the Dopplergrams. So one can see here that in the locations P and K, there one can see the brightenings, which is equivalent to the peaks shown here in the surface map of velocity. So one can see very high velocity flows were seen during the flare in these locations, which shows the local seismicity of the sun. And even the flare of this X3.4 class has given evidence of local seismicity in the sun, not only a flare of X17 class, which we saw in the case of 28 October 2003 flare. So now again, we try to see if this flare has also given global seismicity in the sun. So then we used the data from GOLF, because GOLF is a mission on SOHO, which is dedicated for sun as a star velocity observations, taken in velocity as a Dopplergram using the Doppler concept. And also we use the disk integrated Dopplergrams from GONG for this 13 December 2006 flare. And this shows the progress of the low degree velocity as the time progressed in the flare. This is the location showing the flare maximum. So one can see here the velocity, progress of velocity flows, velocity oscillations for the global modes. And just after the flare, one can see enhancement in the global modes of oscillations of the sun. So then we analyzed these signals using wavelet power spectrum, which gives information on episodic changes which have happened in the power of the oscillations. So one can see here, as the time progressed, just after the flare, there are high signals of enhanced oscillations seen here, 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 all through. So this gives information that the global modes are also excited just after the flare. And this plot is derived from the same wavelet power spectrum. In the global power spectrum, one can see here the enhancement of power in these two frequency regime, high frequency, and this is the P mode regime. So in this work, we did a detailed analysis of signatures of flare in the global waves of the sun for several flares which happened during the period 11 to 17 February 2011, as seen in the GOES soft X-ray observations. So on 11th February, there were no flares, whereas from 12th to 17th February, there were several flares crowded in our observing window. So this gave us an opportunity to see the effect of flares or compare the flare-driven global waves in the sun with respect to a day where there were no flares. And for the purpose, we used disk integrated velocity and intensity observations of the sun taken by the GOLF and Vertigo instruments on SOHO, which does sun as a star velocity observation, and this does sun as a star intensity observation. So here we show the comparison of spectra during flares versus quiet day. In this window, this is the comparison of a power spectrum for 11th February and 12th February. The red the plot shown in red color is for the flare day, and the plot shown in blue color is for the quiet day. So here one can see that there is a significant enhancement of the P modes as well as some high frequency components during the flare, on the flare day with respect to the quiet day. And similar is the case for 11th and 13th February comparison. This blue is for the quiet day, and red is for the 13th February, where there were flares. One can see here this nice enhancement in the power on the flare day in the P mode regime, and also in this 3.3 to 4 millihertz regime. Here one peak is seen. So then we can see here that the global modes, these are the power spectra for the global modes on the flare day, and how these are significantly enhanced with respect to the quiet day. Again, I show here the comparison between the non-flare day and the flare day, 14th February. So the plot shown in red is for the flare day, and the plot is in blue is for the quiet day. One can see that the power spectrum has a wide and enhanced envelope. The whole frequency regime is enhanced, as well as in the high frequency also we see signatures of these enhancements during on the flare day. This is for the comparison between 11th February and 15th February. And again, we can see here the power enhancements in the P mode regime and high frequency regime with respect to the flare day, quiet day. That means the power is enhanced on the flare day with respect to the quiet day for the global modes of oscillations of the sun. Again, similarly here for the comparison for 16th February, the flare day and the quiet day, we can see here again signatures of enhanced power in the global modes of oscillation. Well, here one can see nicely, the nice peak has come up, 2 peaks in the high frequency zone and in the P mode zone. In both the bands, one can see enhancement in the power. So here I summarize the findings and future studies. So what we see in our findings, the power spectra during the flares show about 20 to 60% variation in the power of P modes in the regime of 2.2 to 5 millihertz, and about 12 to 23% variation in high frequency band, 5 to 8 millihertz relative to the quiet day. However, we could not establish a unique relation between the strength of flares and the enhancement in the power of global modes in the sun. Our conjecture is that there is a possibility of other factors influencing the power of global modes of oscillations during the flare apart from the flare energy, such as sudden changes in the global configuration of solar magnetic fields leading to impulsive changes in Lorentz force. Because during the flares, what happens, the global structure of the magnetic fields change, and if there are fast changes, then that can lead to impulsive changes in the Lorentz force for the whole sun, because there are many active regions and there are many magnetic fields here and there, and flares are happening. So there is a global change in configuration of magnetic fields. Then and those are fast. Then the impulsive changes in the Lorentz force can also affect apart from the flare energy, and that can happen for any class of flares. So that's what we are not finding a unique relation between the strength of flares and enhancements in the power of global modes, rather than it can be depending on other factors too, just like the impulsive change in Lorentz force. However, these results are very important because these can suffice in identifying the astroseismic signatures of stellar flares and magnetic activity in sunlight pulsating stars, for which we should have velocity Doppler observations of the flaring stars. So we can try to identify the astroseismic signature of flares in those flaring stars which are pulsating like sun. And thank you for your kind attention.